In the previous lecture, we were given an introduction to vectors. And so in this lecture, we're going to introduce some more concepts relating to vectors. In particular, we've already learned about vector addition and subtraction, as well as the opposite or negative of a vector. We would like to understand multiplication between two vectors. And in this section 11.3 as well as 11.4, we will be introduced to two different forms of multiplication between vectors. In 11.3, we're going to focus on the dot product and probably its most common application, which is projections of vectors. So let's go ahead and get started. First, what we're going to do is define the dot product. We're going to assume that we have two vectors, u and v, and we're going to assume that these are in R3, although this exact same definition holds for vectors in R2. Their dot product is defined as the following. We pronounce this here as u dot v, so that little dot in the middle is literally pronounced dot. U dot v is the following. We take the product of the first two components of u and v, which I've highlighted here, multiply them together, add them to the product of the second two components plus the product of the third two components. So we're just multiplying component-wise and then adding them all together. Something that is very important here is that this dot product, by definition, is the sum of scalar multiplication. So this outputs a scalar. So to reiterate, the dot product inputs two vectors and outputs a scalar. That's an important thing to keep in mind. So let's just do a quick example of computing a dot product. In this example, we have two three-dimensional vectors named u and v. We want to find their dot product. So I want to find u dot v. Again, being careful to always denote the vectors with a hat. When they're written in text, they're written in bold, but since I can't write in bold, then I'm going to use the vector notation. I'm going to take the first component of u, which is 4, multiply it against the first component of v, which is -1, and then I add on the product of the second components plus the product of the third components. So what I have here is -4 plus 14 plus 6. So that's 10, and that's a -6. -6, so I have 10 minus 6 gives me a total of 4. So that dot product input the vectors u and v and output the scalar number 4. We have several properties here for the dot product. We're going to assume that u, v, and w are all vectors. Again, we can assume R2 or R3 or really whatever dimension we want. And let's assume that k is a scalar. So first of all, the property 1 says that the dot product is commutative. So the order in which you dot these doesn't matter. That's just a direct property from the fact that if we look back up top here where our definition of the dot product is, if I switch the order of multiplication of two scalars, it doesn't matter. So same thing here. We also have that the dot product is distributive. So I can either add v and w first and then dot it with u, or distribute the dot product of u to v and w and then add them together. If we have a scalar multiple of a dot product, that is the same as scaling one of the vectors but not both. All right, so it's very similar to if you had real numbers a times bc, you can think of that as abc, but it's not AB times AC, for example. You wouldn't scale both of those other scalars, right? So it just goes to one or the other. Property 4 says that if you dot a vector with itself, you actually get the square of its magnitude. So they write that in two different ways. Either v dot v is the magnitude v squared, or magnitude v squared is the square root of v dot v. So either way. And then of course, whenever you dot the 0 vector with any other vector, you get out the 0 scalar. So you'll notice that this first 0 is bold because that's assumed to be a vector. The second 0 is not bold because that's the scalar 0. All right, so most of those properties are not surprising. They're what you would expect. That brings us to our next theorem, which gives us a way to utilize the dot product in order to find angles between vectors. So we have if u and v are non-zero vectors in 2 or 3 dimensions, and if theta is the angle between those vectors, then we can express cosine of the angle between them as u dot v divided by magnitude u times magnitude v. Oftentimes, what we like to do is rewrite this in terms of just the angle theta. So if you just apply the cosine inverse function, we get theta equals cosine inverse of u dot v over magnitude u magnitude v. And again, I just want to emphasize, be sure you're using double bars to denote magnitude. Single bars are an absolute value, which is not defined for vectors. We need the double bars to denote the magnitude there. This is another way to write this formula. If you just multiply those magnitudes over to the angle, and to be honest, this is how I remember this formula, that u dot v is magnitude u, magnitude v cosine theta. So whichever way you like to memorize it is fine. These are all equivalent, but just make sure you remember that we're working with the cosine of the angle, not the sine of the angle. A couple more remarks here for some information that the dot product provides us with. If u and v are non-zero vectors, then we know that their magnitude is positive, right? You can't have a negative length of a vector. So as long as they're not the zero vectors, they have some kind of magnitude. So from there, what we have is u and v are perpendicular, also known as normal or orthogonal, if and only if u dot v equals 0. So if you think about this for a moment, this is because we know that the dot product is related to the cosine of the angle. So if the angle is 90 degrees, we know that cosine of 90 degrees is 0, thus the dot product equals 0. So this is a quick way to check if two vectors are perpendicular to each other. Then similarly, u and v are obtuse if and only if u dot v is negative. So if we get a negative dot product, we're obtuse. And they're acute if and only if u dot v is positive. So we can just quickly compute this dot product as we saw above. It's a quick computation. And from there, we can identify whether we're obtuse, acute, or perpendicular. All right. So let's roll right into the next example. We want to find u dot v, and in these examples, we do not have the component forms of the vectors, so we can't use the direct computation of the dot product. Instead, we're going to use what we had up here. Let me highlight it, that u dot v is magnitude u, magnitude v cosine theta. So let's go ahead and compute that. U dot v is, so I have the magnitude of u times the magnitude of v times cosine of the angle between them. All right. Now in this class, we're not using calculators, and so I will expect you to know these angles. However, if you're like me, I can never remember which one's which. Is this 1/2 or is this root 3 over 2? I know it's one of the two. So you'll see me quite often drawing these reference triangles to help me remember the smaller angle is pi over 6, the larger angle is pi over 3, and then we have the right angle opposite the smallest angle. Pi over 6 is 1, the hypotenuse is 2, and 1, 2, square root of 3. All right, and so how I remember it is, again, the smaller side is opposite the smaller angle. So 1 is the smallest number out of these three numbers, and pi over 6 is the smallest. And then you'll note that 2 is the square root of 4. So we know that 2 is larger than the square root of 3. The largest side is opposite the largest angle. So the hypotenuse is the bigger number, which is 2. And then square root of 3 is what's left over. And then using SOHCAHTOA, we know that cosine of pi over 6 is opposite over hypotenuse. So I'm looking at the angle pi over 6 here. Sorry, did I say opposite? Adjacent over hypotenuse. And so the adjacent leg is pi over 3, square root of 3, and the hypotenuse is 2. So from that, what we have is the square root of 3 over 2. But remember, this is times 1 times 2. And so in the end here, our answer is square root of 3. And I'll box that in to kind of call your attention to it. And then similarly, let's do the same over here. We want to find the dot product. So I'm going to take the magnitude of u times the magnitude of v times cosine of 135. All right, so 135, this is in quadrant 2. And cosine corresponds to the x component. So over in quadrant 2, we're in the negative x-axis. So we know that that's going to be negative. 2 times 3 is 6. And then the reference angle for 135 degrees is 45 degrees. So what that means is I'm going to have the exact same cosine value as pi over 4, except for it's negative. So that's going to be root 2 over 2. And so this would simplify to a negative 3 root 2. All right, so again, just utilizing this formula up above that's highlighted, that u dot v is magnitude u, magnitude v, cosine of theta. All right, so let's move on here. We have another definition starting on the next page. Regardless of whether we're working in 2 or 3 dimensions, the angles between a non-zero vector v and the unit vectors I, j, and k are called the direction angles of v. So in other words, the direction angles are the angles that the vector v makes with the x-axis, the y-axis, and the z-axis. And so those are the direction angles. Sometimes it's useful to take cosines of those angles. So as you may have seen in a physics or engineering course such as Physics 1 or statics, a lot of times we might like cosine or sine of an angle, as it would give one of the components of the vectors. So the cosines of those angles are called direction cosines. So we have a theorem here that talks about direction cosines, theorem 11.3.4. The direction cosines of a non-zero vector, which is given in component form in v1, v2, v3, are the following. Cosine of alpha is the first component, v1, divided by the magnitude of v. Cosine of beta is v2 over magnitude v. And then cosine of gamma is v3 over magnitude v. Then a property of the direction cosines is that they satisfy the equation that cosine of alpha squared plus cosine of beta squared plus cosine of gamma squared equals 1. And that's just a relationship of the distance formula and the fact that we're normalizing each of these components here. All right, so let's go ahead and do an example of finding the direction cosines. Before we do anything, we need to find the magnitude of this vector because each of the direction cosines utilizes the magnitude of v. So let's start by computing that. I have the square root of 3 squared, which is 9, plus negative 2 squared, which is 4, plus negative 6 squared is 36. If I add that up, 40 plus 9, that's the square root of 49, or a magnitude of 7 units. And then from here, we want to compute the direction cosines. So all we're going to do in each case is take each component and divide it by that magnitude. So cosine of alpha is going to be 3 over 7. Cosine of beta is going to be negative 2 over 7. And cosine of gamma is going to be negative 6 over 7. So these scalars are the direction cosines. We'll box those in. And then lastly, we just want to confirm that they satisfy that sum of squares equation. So I want to take 3/7 squared plus negative 2/7 squared plus negative 6/7 squared. That gives me 9/49 plus 4/49 plus 36/49. And sure enough, that gives me 49 over 49, which is 1. So I'll just put a check mark there to indicate that, yes, it does satisfy that equation there. All right. So the final concept that we want to talk about in this section is regarding projections of vectors. And so we have a definition here. If v and b are non-zero vectors, then we define the orthogonal projection of v onto b to be the following. All right, so first of all, let me talk about this notation. Proj obviously refers to projection, and then it's important to understand which vectors are subscripted and which vectors are not. So how this is read is the projection of v onto b. So v is the vector that is being projected, and b is the vector that we're projecting onto. So what I like to remember is that b is subscripted a little bit, right? It's a little bit below. So that means what we're projecting onto, right? It's underneath vector v. And then the formal definition, let me clean this up a bit so that it's not quite so hard to see. The definition is the projection can be found by taking the dot product v dot b, dividing by the magnitude of b squared, and then all of this here in front, this is all just a scalar, right? Remember, v dot b outputs a scalar, and then the magnitude squared is a scalar. So we take that scalar that I just put in parentheses, and we scale the vector b, all right? So remember, we're projecting onto b. So this projected vector is going to either look like b, maybe longer or shorter, or it's going to be in the opposite direction. In that case, that would be where v dot b is negative, pointing in the other direction. All right. Then we say the vector component of v orthogonal to b, all right, is going to be v minus the projection. So what that's going to give us is we're taking this vector and we're projecting it onto a different vector, b, and then if we want to find the other orthogonal component, that's just v minus the projection. So I think that this geometric interpretation is really useful in understanding what's happening here. Again, many of you guys have taken a physics or statics course where you've worked with vector components. Typically what you're doing is you're finding a horizontal and vertical component. The only difference here is instead of projecting onto the x or y axis, we're projecting onto some other vector b, which may or may not be parallel or perpendicular to one of the coordinate axes. So let me kind of change colors here so that it matches. You'll see here that vector b that we're projecting onto is in blue here. And then we have our vector v that we're starting with. Here it is. And so those red little dashed lines are giving you kind of the guideline of how we're projecting. So if we're projecting v onto b, think of it as taking a foot and just stomping down. Here's like my horrible drawing of a foot or a boot, right? And we're just stomping right down on this vector until it flattens to b. And so you'll see this just comes straight down here. And this new vector, which I'll do in a different color so that you can see, is in the same direction as b, but just a little bit longer, right? V was a little bit longer, and so when it projected down, it went past b. Now, if we want to project the other way, orthogonal to b, then we're just going to stomp in this direction, and we follow this other dotted line, and we get this new projection, v minus the projection of b. So we have our two components of v as they relate to the vector b. This is assuming an acute angle between b and v. The second picture here is very similar. We still have our b vector. This is the vector we want to project onto, but you'll notice now that our vector v forms an obtuse angle from b. So now when we take our boot and we stomp down on this vector, we want to stomp it to the floor of b, but now it comes this way. So our projected vector is still parallel to b, but now it's in the opposite direction, right? And so that's just because, again, we had an obtuse angle. Our dot product between obtuse vectors gives us a negative scalar, and that's why it's pointing the other way. Again, if we want to stomp in the orthogonal direction, so I'll have to draw my boot kind of sideways, and I want to stomp this way, then we follow this projection, and we now get this orthogonal vector. So we've now broken down v into two components as they relate to b. All right, so let's do an example here. And what we want to do is we want to compute this algebraically, but then also sketch it geometrically so that we can see these projections here. So in each part, find the vector component of v along b. So in other words, this is asking for proj v along b. All right, and the vector component of v orthogonal to b. So that is v minus the projection. All right, and then once you've found those, we want to sketch v its projection on B, the vector B, and then the orthogonal component of the projection. All right, so let's get started. What I want to do first is just write down this definition. So I'm going to copy this definition right here so that we have it in front of us. So I want that the projection, let me just write it right up here in the margin. The projection of V along B is V dot B over magnitude B squared. And then this whole scalar is going to scale the vector B. All right, so the first thing we need is, well, two things. We need the dot product of V and B, and we also need the magnitude of B. So you can work with whichever one first. Let's go ahead and find the magnitude of B squared. The square just means I don't need the square root over the distance formula. So that's going to be 3 squared plus 4 squared. So that is 9 plus 16 is 25. And then let's also find V dot B. That's going to be 2 times 3 plus a negative 1 times 4. So that's 6 minus 4, which gives me 2. All right, so here's the two scalars that I need. And then finally, I need to find the projection. So the projection of V onto B is going to be the scalar 2 over 25 times that vector B that we're projecting onto, which is 3, 4. So let me go ahead and distribute this in for graphing purposes, just so that I can kind of see the numbers. This is going to be 6 25ths and 8 25ths. Those are really small components. It's going to be tough to plot that accurately, but we'll do our best. And then let's also go ahead and find the orthogonal component. So, or the vector component orthogonal to B. So V minus the projection. So I'm going to take my vector V, which is 2, 1, and I'm going to subtract off the projection. So 2 is the same as 50 over 25. So 50 minus 6 is going to give me 44 over 25. And then similarly, 1 is 25 over 25. So minus 8. And it's a negative 1. So let's add that in. So negative 25 minus 8 gives me a negative 33 over 25. All right, so let me box in these two final answers for both the projection and the vector component orthogonal. And now I want to sketch all 4 of the vectors involved. So keeping with the colors that we were using previously, let's let purple be the vector V. So I want to go 2 in the X and negative 1 in the Y. And let me go ahead and draw that vector and make sure you label it as well. And then let's use blue for B. B is 3 in the X and 4 in the Y. 1, 2, 3, 4 right up here. And this is going to be tough because they're almost perpendicular. They're slightly acute. So the projection when we project down onto B is going to be tiny. So what we're going to do here, let me just draw those little red guidelines. When we step on this onto B, you can kind of see how little it is. So I'm going to highlight here what we're going to be sketching. We're sketching the projection vector, and I'm going to do that in orange. And we want to go 6 25ths in the I hat direction. So 6 25ths is really close to 6 24ths, which is a quarter. So I want to go a quarter in the X direction. And then 8 25ths is close to 8 24ths, which would be a third. So roughly a fourth in the X and a third in the Y is like somewhere right here. So that was a pretty darn accurate graph here when you look at our little guideline. And I'm just going to try to plot this in orange so that you can see it. And I'll label this as the projection of V onto B. So it's just that tiny little orange vector there. I hope you all can see it. Now we'd like to also find the projection orthogonal to B. So what I'm going to do here is maybe I'll use bright green, and I'm just going to draw a bright green line that's perpendicular to vector B. So now what we're trying to do is we're trying to project V onto that green line. So you can kind of see it's just going to move ever so slightly. But without using that as a guideline, let's look at what we found here, which I just also highlighted in yellow, that projection vector. What color should we do this one in? Let's do magenta. Okay, so we want to go 44 over 25. So that's not quite 2. Is it close to 1.5? Half of 25 is 12.5. So that would be what, 37? A little over 1.5. So between 1.5 and 2. So I don't know, maybe like right there on the x-axis. And then negative 33 over 25. So that's, I don't know, about 1 1/3 maybe. So maybe like right here. And so if we come down, it's somewhere right, oh, you can hardly see it, somewhere right along there, right? My graph isn't completely accurate, but it looks something like this. So in the magenta, this is V minus the projection of V onto B. All right. So again, I apologize for that orange vector being so tiny, but you can kind of see how it's being flattened either toward B or perpendicular to B. I'll leave that up in case people are still copying. But we just want to do the exact same thing here for example 24b. I'm going to start by finding the magnitude of b squared, which is 1 squared plus negative 2 squared for a total of 5. And then let's find the dot product v dot b. That's 4 times 1 plus 5 times negative 2. And that's 4 minus 10, which is a negative 6. So in other words, v and b are obtuse in this case. So we're going to head in the opposite direction. That's why we have a negative there. All right, so let's pull it all together and let's find the projection. Projection of v onto b is the dot product, negative 6, divided by that magnitude squared, which is 5. And then we want to scale vector b, which is 1, negative 2. And so for our projection, we get negative 6/5 and positive 12/5. So there's our projection vector. I'll box that in. And then let's find the vector component orthogonal to the projection. So that's going to be vector v, which is 4, 5. Take away that projection, negative 6/5. Can I squeeze it in? 12/5. And so let's see what we have. So 4 is the same as 20/5, and we have minus a negative, so plus 6/5. And 5 is this, oops, let's fix that. This should, oh no, I had it right. Sorry. It's fine. So 5 is the same as 25/5. Take away 12/5. And so what we get is 26/5 and 25 minus 12 is 13/5. Okay, so we're done with all of the computations. Now we just want to visualize this geometrically. I'm going to try to stick with the same colors here. So vector v was in purple. So we want to go over 4 and up 5 right here. Vector b was in blue. We want to go over 1 and down 2. So these are nice and separated. And what I'm going to do here is just kind of draw these guidelines for B. And I'll also, let me see what color I did last time. I did bright green. Let me draw in the orthogonal guidelines for B. All right. And so now let's go ahead and graph the projection. So first we'll do the projection of V onto B. So I'm looking right over here at these numbers. I want to go -6/5 in the x direction. So that's a little more than 1. And then +12/5. So right around 2.5. So somewhere around here, and then 2 and a little less than 2.5. So that comes up to right about here. Okay. And so here is the projection of V onto B. All right, and then what color did I use? I used magenta for the orthogonal component. All right, so now again, I'm looking at this vector down below that's boxed in. I want to go 26/5. That's a little over 5. So in the x direction, just past 5, maybe right there. And then 13/5 in the y direction. So a little over 2.5, somewhere around there. So if we come all the way over, it's like right here. And there it is. So you can really see these projections in this rectangular box right here. All right, so that concludes our example with projections. We're going to end this section by doing an example from physics. Again, also if you've taken an engineering statics course, you've likely seen it in there as well. All right, so recall from physics that the definition of work produced on an object is the force times the distance. We're going to utilize our information of the dot product in order to compute work. So here, a definition, we're going to let F be a force vector. If we assume that an object moves along a line from a point P to Q, then the vector PQ is called the displacement vector for the object. So again, from P to Q, we can determine that vector PQ. Let theta be the angle that the force vector makes with the displacement vector. Then the work W done by F on the object is the following. So you'll notice that we have two different definitions here. The work, which you'll notice is not bold because it's going to be a scalar number, can either be thought of as the force vector dotted with the displacement vector PQ, or if you use the fact that U dot V is magnitude U times magnitude V cosine of the angle between them, we have the magnitude of F times the magnitude of PQ, again, times cosine of the angle between. So these are equal. These are all representing work, and you can pick which rendition of work you want to use. If you're given your vectors in component form, then the dot product setup is going to be better for you. If you're given more the magnitudes and angles, then the middle equation is what's going to work. So you'll have to decide which one works on a case-by-case basis. So let's do two examples to finish out this lesson. We want to calculate the work done. Problem 38 from the text says, find the work done by a force of -3 pounds applied to a point that moves on a line from 1, 3 in the Cartesian coordinate system to the point 4, 7. Assume that distance is measured in feet. All right, so the first thing you should ask yourself is, which rendition of the work equation am I going to use? Do I want to use the dot product, or do I want to use the angle format? And so in this case, I don't know the angle at all of these forces. However, I can recover the component form. So first of all, I'm just going to write F in component form. We have 0 in the I and 3 in the J. And then what we have here is what I'm going to call points P and Q. And so from here, I can find the displacement vector PQ. Remember, we always take the component from Q minus the component of P. You always take your ending point minus your beginning point. So 4 minus 1 is 3, and 7 minus 3 is 4. Now what I have are two vectors in component form, so I can compute the work by taking F and dotting it with vector PQ. So that's going to be 0 times 3 plus negative 3 times 4. So we get negative 12 foot-pounds is the amount of work done by the force on the object that moves that distance. All right, and our final example, number 40, a boat travels 100 meters due north while the wind exerts a force of 500 newtons toward the northeast. How much work does the wind do? So the first thing we see is we do not have component forms at all in any of these vectors. So this leads us to believe that we probably want to use the fact that work is the magnitude of F cosine of the angle between them times the magnitude of PQ. So let's see what we know and what we need to identify. We know the force of the wind, right? 500 newtons. And we also know that it's going to the northeast. So I'm going to just draw a quick free body diagram here. Northeast is going to be at a 45-degree angle. And so we have this force here is 500 newtons. And I know that this angle is pi over 4. And then we have a boat that's traveling 100 meters due north. So here's our boat. And this distance is 100 meters. So what I now know is since this boat is due north and the wind was blowing northeast, the angle between them is also pi over 4. So I think I have everything that I need here to determine what we have. I know that theta is pi over 4, for one. I know that the magnitude of F is 500. And what else do I know? I know that the magnitude of PQ is 100. All right. And so what we get here is W equals 500 times cosine of root 2 over, excuse me, getting ahead of myself. Cosine of pi force times 100 is the distance that it's traveling. So that is 500 times root 2 over 2 times 100. So 500 cut in half is 250 times root 2 times 100. So add a couple zeros and I get 25,000 root 2. And what am I looking at? I'm looking at Newton meters, which you can leave like that, or you could write that as joules. All right. So that's a wrap here on the dot product. Our next section is going to talk about the other product between vectors,